So today we are glad to hear Felix Ahlborn from the Max Planck Institute for Astronomy in Garching. Felix is currently doing his PhD on the topic of Reynolds stress models for convection in stellar evolution models, and he's doing that under the supervision of Achim Weiss. But he was not new to stellar physics when he started his PhD, because he has done his bachelor and his master thesis both in the SAGE group, the Stellar Ages and Galactic Evolution group, under the supervision of Saskia Hecker. The work he's done there was about mostly rotation in red giant stars, and he has published a paper in 2020 about this work. But currently, he is doing his PhD that he will defend in the beginning of next year, 2022, and he will be looking for a postdoc, most likely to start in fall 2022. So today he will talk about his PhD work, which tackles the very difficult issue of implementing an effective model of turbulent convection in a one-day stellar evolution code, namely Garching, including dissipation by gravity waves. From this work, he is currently writing two papers, one as first author and another as a second author, to be published this year on this work on convection. So Felix, the floor is yours. You can start sharing your slides.
Okay, I hope you can see my slides now.
Yes, very well.
Okay, very good. Thank you, Rita, for this nice introduction. And I would also like to thank the organizers of the seminar series for having me here today. And yeah, as said, I'm Felix. I'm a PhD student of Achim Weiss at the Max Planck Institute for Astrophysics. And today I'm going to present you results from my PhD project, which concerns the implementation of a turbulent convection theory into stellar evolution models. To get started, I would like to briefly remind you of what kind of convection zones we expect in stars. So I've made here two sketches where the left sketch is representative of the lower mass stars below about 1.5 solar masses, like our sun, for example, which have a radiative core and a convective envelope. And the right sketch is representative of the intermediate and higher mass stars, which have a convective core and a radiative envelope instead on the main sequence. So convection is a very important aspect of stellar evolution in several ways, because it's first of all, it's of course responsible for the transport of energy in stars. So it determines the thermal structure of the star. And then the convective flows, of course, also transport elements. So therefore, convection is also determining the chemical structure of the star, at least to a large degree. And so in intermediate mass main sequence stars, the convective region also coincides with the region of nuclear burning. So here the size of the convective core has a direct impact on the energy release of the star or the luminosity of the star. So in this respect, stellar structure and evolution theory needs to answer a couple of questions, like how large is the size of the convective core, how large is the well-mixed region, how does this mixing process look like, and what is the temperature structure in that region. And so in this talk, I will mainly cover the convection in main sequence stars of intermediate mass, so between 2 and 8 solar masses. So how does this convective boundary look like from a theoretical point of view? So in this figure in the upper panel, I illustrate, or in both panels, I illustrate the convective core of a 5 solar mass main sequence star. And the upper panel shows the relevant dimensionless temperature gradient in the star, which is the radiative gradient, the gradient which would be achieved if flux would be only transported by radiation, shown with the blue line, and then the adiabatic gradient, which is the gradient which would be achieved by adiabatic motion, shown here with the orange line. And then at the point where the adiabatic gradient equals the radiative gradient, this is also known as the Schwarzschild boundary, or the point of convective neutrality. So simplistically speaking, one could say that within the Schwarzschild boundary, there is convective driving or acceleration of the convective motions, and outside there is convective damping or deceleration of the convective motions. Now, the lower panel shows the kinetic energy of the turbulent motions in the mixing length picture, which is one of the most common theories to describe convection in stars. And in the mixing length theory, the convective motions are very closely related to the Schwarzschild boundary, and you can see this here. So the convective motions, or the convective energy, directly stops at the Schwarzschild boundary. And effectively, this means that the velocity drops to zero at the same point where the acceleration drops to zero. Now, however, this mixing length picture is slightly unphysical. So from a physical point of view, you would, of course, expect that the flow arrives with a finite velocity at the Schwarzschild boundary and then overshoots beyond that boundary due to its own inertia until it is finally braked in the stably stratified medium. So in this figure, the upper panel shows exactly the same quantities as before. However, the lower panel now shows the convective energy in a more physical picture. And now you can see that the convective energy also extends beyond the Schwarzschild boundary. And as I said, convection is very efficient in mixing chemical elements, so we would also expect that the region beyond the Schwarzschild boundary is mixed by this convective flow, and therefore the convective core would be essentially extended. The problem with that is, however, that mixing length theory cannot compute this region because convective energy is so tightly related to the Schwarzschild boundary. So as I have already pointed out, one important consequence of convection is the convective mixing. So therefore, the effects of overshooting are mostly seen by a modification of the chemical composition of the star. So therefore, one idea to include the effects of overshooting is to add extra mixing beyond the formal convective boundary, beyond the Schwarzschild boundary. So this figure shows two hydrogen profiles of a 5 solar mass star, where the yellow one has been computed using mixing length theory, and then the black one has been computed with mixing length theory plus additional extra mixing, while I've here used the model from Freitag et al. 1996. And if you look in the lower left in this plot, you can see in both profiles a plateau of a homogeneous composition. So this refers to the well-mixed region of the convective core. And of course, for the extra model, this well-mixed region is larger than in the mixing length model, as it was intended by construction. So, however, the problem with that is, of course, that this extra mixing model has no predictive power on the mixing extent or on the thermal structure. And underneath, convection is still described by mixing length theory, and it's just mimicking the consequences of overshooting by adding this extra mixing. So this question of the convective core size becomes, for example, observable when looking at the isochrones of stellar clusters. So in this figure, I show a color magnitude diagram of an open cluster with two isochrones plotted on top of the observations. So the solid line has used a model including extra mixing, and the dashed line is a model without extra mixing. And if you look at the turn-off region, which I marked here with the blue arrow, you can see that the model including the extra mixing actually matches better to the observations than the model without. And of course, further observational evidence for overshooting can be obtained from the detailed observation of individual stars and binary system. So in the left figure, I show results from astroseismology, which you are all probably very familiar with. So by using the individual stellar oscillations, you can determine best fitting model, and then in this best fitting model constrain the overshooting parameter. And the results are shown here as a function of the stellar mass. And you can see that for most models, a non-zero overshooting parameter is required. And in addition, there might be also an indication of increasing overshooting with stellar mass. And similarly, on the right, I show results for eclipsing binary systems. Again, for the binary solution, you can determine an overshooting parameter, which is again shown as a function of the stellar mass. And although the error bars are quite large, you can see that still most models require a non-zero overshooting parameter, and that this seems to be also increasing the stellar mass. So from also these kind of studies, you can see that there is a need of convective overshooting. Okay, so I hope that I have convinced you so far that we need a theory to describe this convective overshooting. And of course, it would be here desirable to find a physically consistent theory which could potentially replace these extra mixing schemes. So this theory would need to provide to us the chemical mixing and the thermal stratification. And to obtain this, we actually need to compute the convective energy profiles and the convective fluxes. Now, the main problem with this is that stellar matter has very low viscosity and in turn very high Reynolds numbers. And this means that the convective flows are highly turbulent. And as you probably know, turbulence is a difficult matter to treat in any context. So this requires a lot of modeling. And then one approach, which is becoming more and more popular, are, for example, 3D simulations of stellar convection. However, these simulations often do not reach the required physical parameters of the convective flows, and they are also quite computationally expensive, which is basically due to a mismatch of the convective timescales, which is on the order of days or months, versus the stellar evolution timescale, which is on the order of at least a couple of million years. And on the other hand, there are these 1D stellar evolution codes who can easily cover the whole evolutionary sequence of stars. And so the aim of my PhD project was the self-consistent computation of convective overshooting for cores in a 1D stellar evolution code using a turbulent convection model. And so in the following, I will introduce you to a specific turbulence model and then also show you some first results for intermediate mass main sequence stars. Okay, before I go into more detail into the theory, I would also like to briefly mention a couple of or range of approaches that have been suggested to be included in 1D stellar evolution codes. So first of all, there are the extra mixing schemes, which I have mentioned already. For example, in the exponential flavor or in the step overshooting flavor. Then there is the rather large family of so-called Reynolds stress models. So these are usually sophisticated models of additional partial differential equation, which try to solve for the structure of the convection zone. And here I would like to mention, for example, the work by Canuto, who has published an extended Reynolds stress model or from the Chinese group from Zhong. And also here the Kufuz model, which has been developed at MPA and which is actually the turbulent convection model, which I use in my project. Then there is a second family of models, which are here denoted by turbulent convection models. These are models which are a bit more simpler than the full Reynolds stress models, and which can be basically derived from the Reynolds stress models. And then finally, there is also the family of Reynolds average Navier-Stokes analysis. So this concerns the analysis of 3D simulation data and then numerically averaging these data to get them down to one dimension. And then potentially results from that analysis could be included into 1D stellar evolution models. However, the application of, for example, Reynolds stress models in stellar evolution is very difficult because of the additional number of partial differential equations which have to be solved. So often one has to start from sort of more simplified models, and in that respect, the Kufuz models are moderately simple, and then, or on the other hand, go to simplified applications. For example, only compute a solution for structural snapshots, or only look at parts of the star, like, for example, do an envelope integration. Okay, as I said already, the method of choice in my PhD project are the so-called Reynolds stress models. And the main idea of Reynolds stress models is to first average quantities over 2 dimensions. So this is highlighted here for the first point for the density, which is integrated over solid angle and thereby averaged such that it only depends on the radius. And then in addition, split the hydrodynamic quantities like velocity or density into a mean part and the fluctuating part. And this is now shown here with the second point. And of course, for us, the fluctuating part is the interesting one, because this is the component of the flow which is due to the turbulence, and then the mean part usually gets neglected. So by inserting these fluctuating parts, or by inserting the Reynolds splitting into the hydrodynamic equations like Navier-Stokes equations, energy conservation and mass conservation, one can derive the dynamic equations for the fluctuating parts, which we then require for our convection model. And further, to derive the convection model, we also need to derive a set of, or define a set of convective variables. So in the Kufuz models, these are the convective energy, which are the square of the velocity fluctuations, the convective flux, which is a correlation function of velocity and entropy fluctuations, and what is called in this context potential energy, which is the square of the entropy fluctuations. And then again, using the hydrodynamic equations, one can derive the evolution equations for these 3 quantities. And in the following, I will be mostly focusing on convective energy and convective flux, because for the stellar model, these are the 2 most interesting quantities. Okay, this brings me already to the first flavor of the Kufuz theory. So depending on the number of assumptions and approximations made in the model, a different number of variables and in turn equations is needed. And so the most simple version of the Kufuz model is what I call the one equation model. And as the name suggests, this model consists of a single nonlinear partial differential equation, which solves for the convective energy. And I will discuss here the terms now in a bit more detail. So first of all, there is on the left-hand side the time derivative of the convective energy, which is accounting for the temporal variations of the convective energy. Then there is the first term on the right-hand side, responsible for the buoyant driving, and it is containing here the convective flux pi. And to keep this model as simple as possible, this convective flux is now again approximated. So Kufuz has modeled this flux proportional to the temperature stratification, nabla minus nabla adiabatic. And if this looks familiar to you, so this is a very similar expression as in the mixing length theory, actually. Then the second term, which is the dissipation term, This has been modeled by Kufuz following a Kolmogorov cascade of turbulent dissipations, so which means that energy is transferred to smaller and smaller scales until it is finally dissipated at the viscous scale. And this can be represented by this expression down here with a dissipation length scale lambda. And in this model, it's usually parameterized as in the mixing length theory with alpha times pressure scale height. And I will come to problems with that expression later on. And then finally, the third term on the right-hand side, this is the what is called non-local flux term. This term is arising from the nonlinear terms in the Navier-Stokes equations. And this is also a model. So if you look closely, this looks like a diffusion term. So there's the gradient of the convective energy. And then in front of that, there is something which looks like a diffusion coefficient. Okay, so now in this model, there have been also at 3 points, basically turbulence models introduced. And at this point, at each point, a parameter had to be introduced. And these sort of approximations are also called, for example, closure relations, because they close the system of equations and make it actually solvable. So now we have a single equation for the convective energy, which is closed, and we can now put that into our stellar evolution code. So as already mentioned in my project, I used the Garching stellar evolution code, or GASTEC in short, which is a 1D stellar evolution code, which uses an implicit solver and a Henry scheme, as most modern codes do. And so we have implemented the Kufuz model into GASTEC, such that the code now solves for the 4 stellar structure equations, and in addition, 1 to up to 3 convection equations. And this work has been already started earlier by another PhD student, so I didn't had to start from scratch here, which would have been much more work. Okay, and then finally, the code solves for up to 7 partial differential equations simultaneously. And each converged model provides us with the stellar structure and the structure of the convection zone in addition, such that the models then can provide us with the temperature gradient computed from the convection model and also the chemical mixing deduced from the convection model. Okay, this brings me now to the first results from the 1 equation model. So these are again results for a 5 solar mass main sequence star, and I here compare a 1 equation non-local model and a 1 equation local model. So local in this case means that the diffusive term gets omitted, such that overshooting is inhibited in this model. And so you can see that the local model, which is shown with the yellow line, this actually stops at the Schwarzschild boundary, as we've seen it in the mixing length picture, while the 1 equation non-local model, which is shown with the red line, extends beyond the Schwarzschild boundary into the stably stratified region. And as outlined in the beginning, this extension beyond the Schwarzschild boundary will also mix chemical elements, and so therefore the convective core will be effectively enlarged. So this means within the 1 equation non-local model, we can see that overshooting emerges consistently as a solution of the convection equations, which is, I think, very nice. Okay, as I've pointed out already in the beginning, also the thermal structure of the model is very interesting for us. In the convection model, we compute the temperature gradient from this formula, which is shown here. And this is understood as follows. So if there is no convective motions or no convection, which means we have a 0 convective flux, then the temperature gradient equals the radiative gradient. And if we have a non-zero gradient, if we have a non-zero convective flux, then the temperature gradient will be modified accordingly. And so in this figure on the left, I show you the temperature gradients in the stellar model in the overshooting zone. where the blue line and the orange line refer again to the radiative and the adiabatic temperature gradient respectively. But in addition, I show with the dashed green line also the model temperature gradient. And what we find is that within the Schwarzschild boundary, the temperature gradient is nearly adiabatic, but slightly superadiabatic. And then beyond the Schwarzschild boundary, we find that the temperature gradient is still adiabatic, but now slightly subadiabatic. And then as soon as the limit of the overshooting region is reached, which is shown here with the black dotted line, the temperature gradient drops very sharply to the radiative value again. So now this brings me to the more sophisticated version of the Kufuz model, which is the 3-equation model. As explained in the 1-equation model, we need to approximate the convective flux. However, the convective flux is a very important quantity for the stellar model. As you've seen, it's needed to compute the temperature gradient. And so therefore, it would be very beneficial to release this approximation for the convective flux. And to do so, one could use another dynamical equation to solve for it. And so when you derive this dynamical equation, you also see that unfortunately a third variable is turning up, which is denoted with the phi here, which I introduced earlier. And so you again need to derive an equation for this quantity as well, and therefore you end up with a 3-equation model in the end. So this model then consists of 3 partial differential equations, which are still nonlinear, and in addition they are also coupled. So you can see that some cross terms are showing up in the equations. So the first equation is exactly the same for the convective energy, which I showed you previously. And then the second and third equations, these are the new ones, and they have a mostly similar structure. So some source and sink terms in the beginning, then the non-local flux terms, which get again modeled in a diffusive way with the introduction of 2 more parameters. And then finally, there are radiative dissipation terms turning up, which also need to get modeled and have a parameter. So now we can put this model into our stellar evolution code again. And so this figure is now showing the first results we obtained from this more sophisticated convection model. It shows the convective energy transformed in a kind of logarithmic way in a 5 solar mass star as a function of the fractional mass. So the red line is the convective energy in the 1-equation non-local model, which we used as a starting model. And then the subsequent blue lines show the time evolution of the convective energy as it is moving through the star until finally at about 1,000 years, a steady state is reached, shown with the blue dashed line. So this would mean that the star is actually fully convective, and due to the mixing efficiency, it would be also fully mixed. However, for a star in this mass range and in this evolutionary state, this does not make a lot of sense. And such a thing could be also ruled out by observations, for example. So the conclusion at this point was that our convection model is actually incomplete and an important physical ingredient is missing here in the model. Now the question is, what is actually missing in the model? So what is going wrong? And then here the first culprit to think of was the dissipation term in the convective energy equation, because too large overshooting extent could be, of course, a sign of missing dissipation in the model. And so to fix that, one would need to increase the sink term. And so in this work, which we are now doing together with Friedrich Kupka, the idea is to introduce the dissipation term proportional to the temperature stratification, so this epsilon proportional to the superadiabatic gradient. And yeah, this could be for example, be the dissipation due to buoyancy waves in the overshooting zone. In our stellar models, we have implemented this through a decrease of the dissipation length scale. So to remind you, this is the Kolmogorov term for the dissipation. And so in the denominator, there is the dissipation length. So by reducing that, one could increase the dissipation. And an alternative interpretation of this decreased dissipation length could be also that the eddy size of the convective eddies needs to be limited. So as they are getting closer to the boundary, this length which the eddies can travel until they have lost their energy is getting smaller and smaller. And so therefore one needs to decrease the scale at which the energy is fed into the turbulent cascade. So now I show you the first results we have obtained with this new dissipation model. So if you first look at the lower panel, this is showing the dissipation rate in the three-equation model. And you can see that, first of all, this dissipation rate is not growing through the whole star, but it stops here at about 0.3 in fractional mass. And there seems to be also a small excess close to the convective boundary. And then the upper panel shows the aforementioned dissipation length scale, which, as you can see, also clearly decreases as it gets closer to the convective boundary, which is, of course, then resulting in the enhanced dissipation. So using this modified dissipation model, we can again compute the stellar models. So this figure is again showing a comparison of the convective energy in a 5 solar mass star for a local model shown in yellow, and now the three-equation non-local model shown with the blue line. And now you can see that actually the convective energy still extends beyond the Schwarzschild boundary, but it is clearly limited, so it stops somewhere around 0.25 in this model. So this means again that now the overshooting is emerging consistently just from the solution of the model equations. And that actually in this model, the dissipation term fixes the problems which we've seen earlier. Okay, given the kinetic energy or the convective energy profiles, we can also compute the chemical mixing profiles. So this is actually done in the same way as for the mixing length theory. So diffusion coefficient is proportional to length scale times the convective velocity. In the Kufuz model, we need to approximate this convective velocity because we only solve for the energy. So here one can approximate for this by assuming isotropy of the turbulence. Now this figure shows the diffusion coefficient as a function of fractional mass for a diffusive overshooting model and the three-equation non-local model. In the bulk of the convection zone, you can see that the diffusive model leads to slightly larger diffusion coefficients, which is mainly due to the higher velocities which are found in the mixing length theory. However, this does not make any difference basically because both coefficients are, they are very efficiently mixing the star, and so these regions with the high mixing coefficient, they are fully mixed anyway. However, in the overshooting zone, more pronounced differences are visible. So the Kufuz model maintains a rather high mixing efficiency throughout the overshooting zone, while the diffusive overshooting model drops off exponentially as intended by construction. So in this comparison, the Kufuz model looks more like a step-like overshooting. And then finally, from these diffusion coefficients, we can again compute the mixing in the stellar interior. So this figure shows again the comparison of the hydrogen profiles for a 5 solar mass star and for a mixing length model, and for the three-equation non-local model. And you can see that the three-equation model now extends beyond the mixing length model, but it doesn't grow throughout the whole star anymore. And also, if you look in the lower left at the well-mixed region, so it's the Kufuz model or the three-equation model is slightly extending beyond mixing length theory. So this looks now very reasonable compared to the previous results we obtained. Okay, so far I have mostly shown you structural models of computed with the Kufuz model. However, we can also do stellar evolution, of course, with this model. So in this HRD, I show you two evolutionary tracks, one computed with mixing length theory and the other one computed with the three equation model. And you can see that the three equation model results in a luminosity which is always higher than the mixing length models, which is a consequence of the increased fuel supply, which we have seen in the previous slide. So this is again an effect similar to the extra mixing. And this sort of comparison also, of course, relates back to the color magnitude diagram, which I showed you in the very beginning, where one could reproduce the increased magnitude at the turnoff with such a model. Now for the three equation model, I would like to go into a bit more detail now to the convective flux, because this is, as I said, also a very interesting quantity for the convection model. So in this figure, I show a comparison of convective fluxes computed with the three equation model and from a diffusive overshooting model, which essentially means convective flux from mixing length theory as a function of the fractional mass. And you can see actually that there is a very, very close agreement between these two models. So the gray dashed line is basically lying exactly on top of the blue line. And these two models, which I have selected, I have tuned them to have the same core size and the same luminosity, but apart from that, no fine-tuning has been to achieve this agreement. So this means that both convection models arrive at the very similar convective flux in the stellar interior. The only small difference which can be seen is, or which can be observed, is around about 0.15 in fractional mass, but this can be much better illustrated by looking at the temperature gradient derived from this convective flux. So given the convective flux from the previous slide, we can compute the temperature gradient. And so this is a very similar figure as I showed it to you previously. The dimensionless temperature gradients as a function of the fractional mass. However, now the model temperature gradient has been computed with the three equation model. So we still find that the convection in the so within the Schwarzschild boundary is mostly adiabatic. You can see that here that the model temperature gradient comes from a nearly adiabatic value in the stellar interior. However, you can already see that it is slightly subadiabatic at the Schwarzschild boundary. And then in the overshooting zone, there is a transition region in which the temperature gradient gradually transitions from the nearly adiabatic to a mostly radiative value, while it takes slightly super radiative values in this transition region. And overall, given this narrow transition region, the overshooting zone has now mostly radiative temperature gradient. And here I would like to point you to results from Michielsen et al. 2021, who also found that radiative temperature gradient in the overshooting zone might be a good fit from an astroseismic analysis. Now one can go even one step further into the details of the temperature gradient. In this figure, I now compare the convective flux shown in the upper panel and the super adiabatic temperature gradient. So model temperature gradient minus adiabatic temperature gradient. And if you look in the region, say beyond between 0.1 and 0.2 in fractional mass, we find a region in which the convective flux is still positive. However, the temperature gradient is already subadiabatic. So this means in this model, the super adiabatic temperature gradient cannot be driving the convection in this region because it's simply subadiabatic. And so something else must be driving the convection, which in this model then are the non-local terms of the convection model. And such a layer is also known as a Deardorff layer or counter gradient layer, because convection is here working against the gradient, and is known from the atmospheric sciences, for example. And such a layer is, however, not expected in simpler convection models, like in the mixing length theory or the one equation model. The temperature gradient and the convective flux are tightly related. And so any layer in which the convective flux has a different sign than the super adiabatic gradient is simply strictly inhibited. And so to obtain this, one needs actually the three equations and non-local terms. Okay, this now brings me finally to the first application we have made of the three equation model. So in this figure, I show how the convective cores behave as a function of the stellar mass for different convection models, which are here from top to bottom: the extra mixing model shown in black, one equation model shown in red, three equation model shown in blue, and then finally simple mixing length models shown in yellow. And this figure allows already some interesting conclusions. So first of all, you can see that with the three equation model, we obtain convective core sizes, which are always larger than the mixing lengths theory. So this means that an overshooting range is emerging from this three equation model across the mass range we have investigated here. And so this is, again, without extra mixing, but just as a solution of the convection equations. And then further, we also find some qualitative agreement concerning the size of the convective core. So you can see that all three models describing overshooting are basically resulting in a comparable convective core size. And then finally, we also see that in our turbulent convection models, the core size is decreasing with stellar mass, that is also expected. However, of course, there are quantitative differences in the models. So while the artificial or the extra mixing models mostly produce the largest cores, at least for the lower masses, the three equation model produces the smallest cores, and the one equation model is somewhere in between. And as the extra mixing model or the parameter of it has been somewhat calibrated to observations, then one might maybe say that the three equation model is increasing a bit too steeply with stellar mass here.
Felix, you have 5 minutes left.
Good, thank you. Okay, and then before coming to the end, I would like to briefly mention one last aspect of the Kufuz model. So as you have seen, it is by no means parameter-free. It has quite a number of parameters, I think 7 in the current implementation. However, not all of these parameters are equally important. And so I would like to point you to the most important parameter, which is the one in front of the kinetic energy flux, which I show you again up here. So this alpha omega turns out to have the largest impact on the overshooting extent, which makes sense, because if you increase the kinetic energy flux, you would also expect that energy or kinetic energy profile moves further out, and therefore you would increase the core size. And so on the left side, I show the turbulent convective energy, again transformed in a kind of logarithmic way for 3 different parameter values. And you can see that indeed for a parameter value of 0.1, you find the smallest core in this comparison, and for a parameter of 0.5, you find the largest extent of the convective energy, which would, of course, then be again imprinted in the chemical profiles of these stars. So the other parameters in the model have mostly more subtle effects, which I will not discuss in this talk today. Now this brings me finally to a brief outlook of things which one could do in the future. For example, What would be very interesting is the comparison of the 1D stellar evolution results to 3D simulations. So this would happen, for example, in the framework of the Reynolds average Navier-Stokes analysis, which I mentioned already. Then one could think of modifying the set of equations. So, for example, introduce another partial differential equation to explicitly solve for the dissipation instead of approximating it. Or introduce another equation to, for example, study the anisotropy of the turbulence. So this is another approximation which Kufuz has made, that turbulence is isotropic. And then finally, which is of course relevant in this audience, is use astroseismology to test the convection model. And here I just have a certainly incomplete list of references. What one could test, for example, extent of the overshooting, mixing profile, or the temperature gradient of the convection model. Now with this, I would like to conclude. So I hope I have convinced you that convection is a crucial ingredient in stellar models, and that especially the treatment of convective boundaries is difficult, and therefore a physically consistent theory is required to describe this. But due to the low viscosity, the convective flows are highly turbulent, and therefore the family of Reynolds stress models offers a good possibility to model these flows and to also include the effects of convection into 1D stellar evolution codes. And so in my project, we have implemented such a convection model into Galactic to self-consistently compute the structure of the overshooting zone, which concerns the chemical mixing and the temperature stratification. And we find qualitative agreement with other methods, and also the decrease of the convective core mass with stellar mass fits well into the picture. And also for the thermal structure, we find that the convection is mostly adiabatic within the Schwarzschild boundary, which means that it is very efficient. So also in somewhat agreement with previous results. Okay, and then finally, we had to introduce this enhanced dissipation mechanism by, for example, buoyancy waves to get reasonable overshooting distances. And with this, I stop, and I thank you for your attention, and I'm happy to take questions.
Thank you very much, Felix, for a very comprehensive talk. So I think we have time for questions. Okay, I see. Okay, Connie has a question, but she will tell us that she would like younger people to ask one. So I encourage young people to go ahead and start thinking about questions. While okay, Dominic, you can start asking your question, and then Connie.
Thanks, Rita. Thanks, Felix, for this. This is very interesting. I think it was slide 26. I had a curiosity.
Let me see. Okay, now it's changing. Yeah, please go ahead.
Could you please elaborate a little bit on what you're comparing here? Are these models of all the same age?
Oh yeah, good question. No, not the same age, but same central hydrogen abundance. So to make this comparison reasonable, I have chosen the central hydrogen abundance as a criterion to compare the models.
Yeah, okay, that's good. So I thought this was very interesting because Andrew Chichenko had a paper looking at eclipsing binaries and the mass discrepancy, which is more of a core mass discrepancy with its effect on age. So I think this prediction couples quite nicely to the observations. But what you're predicting is a decreasing mass discrepancies, if I'm interpreting this correctly. Rather than a decreasing core mass, it's a decreasing core mass discrepancy from the MLT prescription. Is that correct?
What do you refer to exactly as mass discrepancy?
So your conclusion was you have a decreasing core mass with increasing mass, but I think you mean a decreasing core mass discrepancy with increasing mass, in the sense that the underestimated core mass gets smaller with increasing mass, rather than the core mass gets smaller with increasing mass.
Yeah, that is correct. Maybe I wasn't entirely clear. So what I meant is that convective core mass is decreasing with decreasing stellar mass. So as you can see, the cores become smaller and smaller with decreasing stellar mass. So I think this is what you mean, that the discrepancy is decreasing when you increase the stellar mass. Yeah, I think so.
Yeah, okay. So I think to reproduce this plot with different XC values would be very interesting. So I would encourage you to do that, because this problem is an age-dependent problem as well as a mass-dependent problem.
Okay.
But I encourage you to do that. But
Yes,
thanks for this. This is very interesting.
Thanks for the comment.
Connie, I see you've posted something on the chat. I encourage Felix to go and have a look, but maybe you have something to add?
Well, thanks, Felix, for this very clear talk on difficult matter. Congratulations. I'm very interested in this, of course, and I'm extremely pleased to see that people are moving to B stars. So since you have a mass regime that completely overlaps with our slowly pulsating B stars, I've posted in the chat a link to the paper that came out last week by Mike Pedersen. And so there you have actually, I think, the opportunity to calibrate your parameters. You said that one is dominant in your list of 7 parameters, right? But perhaps you could try to quantify that statement from the observational data. And so Mai's paper is unique in the sense that it provides a sample of stars rather than just, one star that may be, may not be representative of a full sample of stars with different velocity, age, and mass. So I think it would be very interesting to couple your numerical and theoretical work to the constraints that we have for the moment, which are to be improved. It's not that we have find the final observational calibration, but it's a first step. So it would be really very interesting if you could do that in the future. Okay.
Okay. Thanks.
If anything is unclear, then just contact us for help.
Okay. Thank you for this comment and for pointing out this paper.
So after Connie, I think Saskia was the next one. Saskia, you want to ask your question?
Yeah, so thanks very much, Felix, for this very great talk. My question actually relates to what Connie just said, because you have these 7 parameters, and I was wondering, how did you choose them at the moment? And if you choose them, you showed one plot where you choose the alpha omega, but how would that impact on your results that you showed today?
Yeah, that's a very good question. So some parameters of the model have been actually obtained by calibrating to the mixing length theory. So as I said, if you omit the non-local terms in the Kufuz model, the model basically drops back to a local model, which is equivalent to mixing length theory, which then allows to calibrate some of the parameters. But of course, for the non-local parameters, it doesn't make sense to calibrate to mixing length theory because because mixing length theory is not providing this. And here at this point, Kufuz has made some theoretical or analytical estimation for the first parameter for this alpha omega, which I showed, like for this one, where about value of 0.3 or 0.25 is sort of the default value. And then we have chosen the other 2 non-local parameters just to have the same value because there is no reference where you could take them from. But this is the impact of the other parameters is also somewhat still to be tested. But so far, it seemed that on the overshooting extent, at least, they have a very little impact.
Great, thank you very much.
Then Jörn, go ahead.
Thank you, Rita, and thank you, Felix, for a very interesting talk. very ambitious and important projects. We all love B stars, don't we, Connie? Especially when it comes to this kind of thing. And of course, the hope is that we can learn enough about convection overshoots also to apply it to, let's say, early G stars or F stars when we determine their ages. Of course, I'm also worried about the number of parameters, and I really wonder how you can calibrate that using the 3D simulations. And also, I was struck by the fact that you get a nearly adiabatic overshoot region, which I think is unlike some of the other formulations. Of course, with the diffusive mixing, you can do whatever you like. There's no physics involved there, so that's easy. I think you should take a closer look at the Yan Li formulation because it's somewhat similar to what you're doing here. And it's been applied quite a lot in the Chinese community, at least. So it's also quite fairly simple and a few equations. So that might be an interesting comparison. And then a question, a technical question about how you do this, because you have the equations for the convection with a time derivative. And that must be on a convective time scale, which is much shorter than the evolution time scale. So it's what you do to solve these equations for each time step and then get a convective flux, etc., at each time step before you continue with the evolution time, follow the evolution time scale.
Well, what we do here is that because this is only giving you the structure of the convection zone in a kind of statistical sense, because the quantities get averaged, we usually, this time derivative can be usually omitted and we solve for the complete or for one evolutionary time step. And because that time step is so large, the changes in the convective energy are so small that this time derivative can be actually neglected. So this is, I think, one of the advantages of Reynolds stress models, because they are effective models of turbulence. So we do not have to solve for the individual small time and length scales, but instead get the overall get an overall statistical picture of the turbulence, and therefore one can do this.
Okay, fine. So the Kufuz equations are simply added to the normal stellar evolution equations.
Exactly, yeah, they are solved.
And solved like that. Okay, that is a very convenient feature. Thank you.
Welcome.
Okay, I see we have no more questions. No more questions. Yes, so we have one question from Atefe. You can go ahead, please.
Yeah, hello, Felix. It's very nice to see you again. I'm not from this community. Sorry if my question is very naive related to this stellar evolution. But my question is that when you, for example, in this equation that you show, you have this alpha omega, which is this diffusion, basically, if I understand it correctly, it's a diffusion coefficient. I would like to know how the rotation can play a role in these models, because as you may know, this diffusion coefficient rotation can actually add anisotropy to the diffusion in general. That makes some changes if you include it or not include it in these turbulent models. So then my question is just like how the rotation, if you have rotation in these models, does it make any effect or not, or how it is?
Yeah, that's a very good question, but also very difficult. So we do not consider rotation in these models. So these are non-rotating models, and hence also rotational transport is not treated. So I really cannot tell what would happen if you include rotation in here. Unfortunately, I'm sorry.
Okay, thank you so much. If you let me ask one more question. That was about this closure that you use for closing this your actually mean field equations. Can you elaborate on that? What was this closure again that they used for this energy transport?
Yeah, okay, let me go back to the slide. So this is shown here. The first line is the convective energy equation. And I guess you are referring to this last term. So this is modeled as a diffusive term, or maybe you're also more familiar to the term down gradient approximation. Originally, this is a correlation function made of 3 fluctuating quantities. And because in the Kufuz model, or mostly in Reynolds stress models in general, one is only solving for the second order correlation functions, one cannot self-consistently solve for this 3 third order correlation function. And therefore one has to introduce this closure, and then most commonly this is treated as a diffusion approximation, because one says, okay, this the third order correlation looks like a flux of a second order quantity, and then this flux of a second order quantity can be modeled using a diffusive approach by saying some diffusion coefficient times the gradient of the quantity itself. Whether this is a good approximation has, of course, to be tested, for example, from 3D models. And there are also other methods around. For example, you could also solve the dynamical equations for the third order correlation functions, but then you are left with additional, I don't know, 7 equations or so, and you don't want to do this actually. But yeah.
Yes, thank you for a very good explanation.
Okay, so I see it's past 11, so I will first thank everyone for being here, and of course Felix for a very, very interesting talk. And then I see there are still a few questions, so people who want to ask their questions can stay around, and people who want to hear the answers too. So thanks everyone, and we'll give the floor to Marcelo. I think Marcelo is your brother, your scientific brother, Felix, if I understand correctly. So go ahead, Marcelo, you can ask your question.
Hi, Felix. Very nice talk, very interesting as always, and I guess you might know what I'm going to ask, but can you have you had the time to explore whether the temperature gradients in the let's say the overshooting region, do they depend on some of the parameters or at least which parameters are influencing how adiabatic or not adiabatic the temperature gradient in this region is?
Well, I don't think I had time to look at that. One thing which came to my mind is, for example, to check the Piclet number, which is telling us something about the convective efficiency. So one could look at that to whether this is explaining the behavior. But no, I had not really time to go into the different parameters.
Okay, thanks.
And one last question for Friedrich, I believe.
Okay, hello. This is just perhaps a comment to Jörn's question concerning how the parameters were calibrated. Well, indeed, some of the model parameters have been calibrated from comparison to turbulence model and to direct numerical simulations in parameter regions that are achievable. So in this sense, currently, it's not such that there are 7 freely floating parameters, and basically a few of them have been calibrated to reproduce local model solutions, and the other ones have been tuned from sort of guesswork, but there actually is for the different parameters at least some guidance from solutions for, say, similar scenarios, like specifically for overshooting. So this kind of input has been actually had to constrain at least a little bit the parameters. So it's not completely without informations from numerical simulations and turbulence modeling and comparing to other flow scenarios, even though, of course, that's a key issue with the model. I just kind of wanted to add this because otherwise the impression is that there's sort of no guidance at all in choosing the parameters, which is, I think Felix would agree, is not the case.
Yeah, that is true. Thanks a lot for the clarification.
Okay. So Vincent Böning, you have one question. I think it will really be the last one.
Okay, thank you. Thanks, Felix, for the nice talk. I just have a question on how the stratification changes. So you have shown how the temperature gradient changes. I'm interested in how the density structure, the density stratification changes. Do you have an idea? Is it just very tiny? Is it, how big is it? Do you have an idea? Or?
Yeah, good question. I have not looked into that in detail. So from my feeling, I would say it's a very small changes, but yeah, I cannot give a definite answer to this.
Okay, thank you.
Okay, so I think we will stop here.
Okay.
So again, thanks a lot, everyone, for showing up and contributing to this questions. And thank you so much, Felix, for a very interesting talk about a very difficult issue, and that is still open, and there's still a lot of work there. So thanks a lot. Again, you can go on our website to check out the past seminars, the videos, the upcoming ones. Next week, we will have a seminar given by, I think it is Thomas. Okay, let me just check. Upcoming, yes, it is Thomas Stendel from Innsbruck University, and he will talk about tidally perturbed pulsations in pre-min sequence delta sq-T stars. Thank you, and see you in 2 weeks.
Thanks a lot.
Thanks, Felix.
See you.
Bye.
Thanks.
Bye, Vicky.